are going to talk about digital counters. First, let's define what a counter is. In digital electronics, a counter is a circuit that counts or stores the number of times an event has occurred, often using a clock signal. Okay, now let's see about synchronous and asynchronous counters. Okay, let's start with asynchronous counters. Also, these are known as the ripple counters. In these counters, the flip-flops are triggered one after the other. It's like a line of dominoes falling. The first one starts and then it makes the next one go and so on. The clock signal goes through the flip-flops sequentially. The first flip-flop changes when the clock tells it to, and then its output triggers the next one and so on. That's why these are called the ripple counters. You can see the properties of asynchronous counters. These are known as ripple counter, and it has cumulative delay. Let's see, cumulative delay limits the operating frequency. Okay, the total time taken for changes to propagate reduces the maximum counter operating speed. Okay, and it's a design also a little bit simple than synchronous counters. You can see the circuit diagram of asynchronous counters. Uh, a 2-bit asynchronous binary counter. Okay, I included a clock signal and two JK flip-flops. You can observe this. Okay, now let's look at synchronous counters. In contrast to asynchronous counters, synchronous counters trigger all the flip-flops at the same time. Like a counter example, racers run it at exactly the same time when the gun fires. Okay, this simultaneous clocking action makes sure that state transition occur in perfect coordination. Okay, these are the properties of synchronous counters. Simultaneous clocking, as I told, and its propagation delay also minimized because they all start at the same time. Because of that, also faster operation is also done, and its design is a little bit complex compared to a synchronous counter. You can say I included a 4-bit synchronous up counter, included clock signal and 4 JK flip flops, and you can see these outputs and again, and you can see this. Okay. Okay, these are the differences of synchronous versus asynchronous counters. Okay, synchronous were faster and more complex and have less time delay, and these are used for high-speed applications because they started exactly the same time. That's the advantage of this. And coming to asynchronous, it is slower compared to synchronous, and but its design is simpler compared to synchronous circuit. Uh, and it has cumulative delay because one start after okay, and low speed application, these are used for the low speed applications. Okay. These are the applications of counters, frequency dividers. These basically convert high frequency input signal to a low frequency output signal, and you can see event counters, it counting occurrences in automation. It basically counts number of events or cycles. And in digital clocks, these are the main parts in formation of digital clocks. And these are used in timers also. You can observe this simple diagram. And these are the counter design considerations. These are used to design a counter circuit. These are the main points. First one is modular selection. We have to choose the number of states of that circuit. And second one is the flip-flop choice. Select among JK, T, or D flip-flops based on their factors like complexity and functionality. Okay, third one is decoding logic. You can design gates for count values, interpret output at each specific state. Okay, and fourth one is state diagrams. This is important to understand. Uh, you can visualize the output, operation, and transition. Use a state diagram to represent the sequence, making it easier to understand the counter's behavior. These are the advanced counter types. The examples are up-down counters. They are used to calculate the increment or decrement in a digit, used as bidirectional counting also. And second one is decade counters. Decade counters are basically decimal based applications. They count from 0 to 9 only. And third one is ring counters. Ring counters use shift registers with feedback. And feedback is basically the output is connected directly to an input of the circuit. Okay. And fourth one is Johnson counters. Johnson counters is basically a modified type of ring counter which improves decoding properties. In conclusion, both asynchronous and synchronous counters play important roles in digital design, each with its own advantages and disadvantages. Like synchronous counters excel in speed and precision, and asynchronous counters offer simplicity and ease of design. And the choice between the two depends on careful balance of speed and complexity, and we have to consider cost also. Okay. Thank you guys. Thanks for watching.